So today in this video, I'm going to do the second part of organometallic compounds. So in the last part, we have stopped up till hapticity, how to find hapticity, oxidation number, etc. So now this is the second part of it, wherein we are going to find out, learn yet another important concept, that is electron contribution. So electron contribution is basically used when we determine the 18 electron rule. So for 18 electron rule, you need to know electron contribution concept. If you are seeing this video for BSc or MSc level, then basically I am going to teach you two methods on electron contribution. So if it is an undergraduate or postgraduate level for which you are watching, you have to know both the methods. But so basically the methods are, one is called as the neutral method. The second one is called as the ionic method. Okay. So basically what it means is that, say if I have a bond between two atoms, like say for example carbon-carbon bond or carbon-hydrogen bond. So basically a bond is formed by two electrons. So electron contribution is basically how much of electron is each atom contributing. Now say for example if it is a carbon-carbon sigma bond, we say one electron is contributed by this carbon, one electron is given by this carbon, and then the same here. So this is for bond formation. But whenever we talk about electron contribution, we need to check how the bond will break. So there are two methods by which we can break a bond, either through a homolytic cleavage, which is what is the concept of neutral method. So if you break a bond through homolytic cleavage, it comes under neutral method. Now if you break a bond through heterolytic cleavage, then that comes under ionic method. Okay. So say for example, you have a carbon hydrogen bond. There are two atoms, okay, two electrons. Now if I have to see do a homolytic cleavage, you would have done it in a free radical formation by placing fish hook arrow. Each atom gets one radical, right? So this carbon is going to have one electron, this hydrogen is going to have one electron. Then we say that the electron contribution of this carbon is 1, the electron contribution of this hydrogen is 1. This is what is neutral method. So basically the number of electrons used between the two atoms is broken equally among the two atoms. So you say for example if you have a double bond, then what you do, you are having 4 electrons, right? So this carbon would get 2 electrons, this carbon would get 2 electrons. Now this is called as a neutral method. So if you are seeing this for your basic undergraduate or postgraduate level, you basically need to know both the methods. But if you are preparing for a competitive exam like JAM exam or CSIR NET or GATE exam, the best method which does not have any complication is the neutral method. So if you calculate the electron contribution through neutral method in OMC, it is going to be much easier. Now in case of ionic method, what we do, say for example, so this is organometallic compounds, right? So basically there is going to be a bond between a metal and carbon. So there are two electrons here. So in neutral method what we do, we will break it homolytically such that each of the atom gets one electron. But in heterolytic cleavage, we need to see the electronegativity, just like how we saw for the formal charge in the last part of the video. So if you have not seen that, please do see that and come here so that you will have a clarity. If you see here, there are two electrons, right, between metal and carbon. Now we need to see which is more electronegative. Now we know that carbon is more electronegative than metal. Any metal you take, carbon is more electronegative. In fact, we also saw that in case of iron hydrogen example, even hydrogen is more electronegative than most of the metals. So whenever you have a organometallic compound wherein you have a metal carbon or a metal hydrogen bond, the carbon is going to be more electronegative. So both the electrons are going to be cleaved heterolytically towards carbon. So the metal is going to have a positive charge and carbon will have a negative charge. In heterolytic cleavage, what happens? Always there is charge formation, right? Because you are breaking the bond uneven. So whenever there is an uneven breaking of the bond, there is going to be charge formation. So metal will get a positive charge and carbon will get a negative charge, which means what? Negative charge denotes 2 electrons. Both the electrons between the bond has shifted to carbon. So the contribution of this carbon in the metal carbon bond formation is 2 electron through ionic method. But if the same thing you do it through a neutral method, you don't have to think about the electronegativity. You simply see 2 electrons, break one towards metal, 1 towards carbon, and you say the electron contribution is 1 electron. So this is the basic difference between the neutral method and ionic method. Okay. Now when we do some examples, you will start understanding how we have to apply this. Okay. Now whenever you have a sigma bond formation, so the first rule here is that whenever you have a sigma bond or pi bond formation between metal and carbon, break through neutral method or ionic method, or you can say electron contribution can be determined through neutral method. I will denote it by N, okay, and ionic method I will denote it by I. Okay, so neutral method or ionic method. So whenever you have a sigma or a pi bond, there only this rule is applicable, which means what? Say for example, now I told you carbon metal bond. So this is a sigma bond. You can also have carbon double bond M. So this is a pi bond. So in these cases, you can use neutral method or ionic method to determine the number of electrons that is there. Now here what we do? So you basically have to find out how many electrons is being contributed by this ligand. So here carbon is the ligand, right? So in neutral method what you do? There are 2 electrons here. There are 2 electrons here. So what you have to do? You have to break the bond homolytically. So the electron contribution is going to be 1. Okay. Now in this case there are 4 electrons here. So you have to just divide it equally. So from this bond 1 electron goes to carbon. From the bottom pi bond 1 electron goes to carbon. So the number of electrons contributed by carbon here is going to be 2. Now in ionic method what we do? We find out the electronegativity. So carbon is more electronegative than metal. So both the electrons will move towards carbon. Okay. So the number of electron contribution by carbon is 2. Now here again you have totally 4 electrons. So all 4 electrons are going to move towards carbon because carbon is more electronegative. So the electron contribution is 4. This is also true for a triple bond also. Okay. So whenever you have a sigma or a pi bond directly between a carbon and metal, you can use either neutral method or ionic method to determine the electron contribution, and it will be changing. So neutral method you will have one type of answer, for ionic method you will have another type of answer, and that does not matter. But the second rule is that if there is a coordinate bond, coordinate bond means what? It can either be through lone pair or pi electrons or sigma bond. Then electron contribution is always equal to 2. So this is very important. Either you do it through neutral method or ionic method, the electron contribution is always going to be equal to 2. Now what does this mean? Now you say I have a metal bonded with ammonia. Okay. Now I know that ammonia, that is NH3, nitrogen can form only 3 bonds. So basically already it has formed all the 3 bonds with nitrogen. So hydrogen. Now nitrogen has one lone pair of electrons with it. Now this lone pair of electrons, it is donating to metal. That is why we call it as a coordinate bond, right? Basically it is not an equal contribution like you see here. It is basically the donation of nitrogen, okay, to the metal to form a bond. So basically the 2 lone pair of electrons are being donated. Now in this case the metal and nitrogen bond, if you have to break, you can't break it homolytically because there is no contribution from the metal. Okay, so that didn't give anything for this bond formation, then how can it take away the electrons, right? That is unfair. So what you do in those cases is that whenever there is a bond formation through lone pair, such as this case, or we saw some examples in the last video, right? Say for example, you have a pi bond formation. That means that these 2 carbon, the pi bond between the 2 carbon atoms is donating its electron to the metal. Or we also saw this example wherein the sigma bond of hydrogen is donating its electron to the metal. In all these cases, these 2 electrons that is being donated to the metal, that should be considered as the electron contribution. Okay. So, the ligand is contributing the 2 electrons that it is having in the bond. So, in those cases you do not break the bond through homolytic or heterolytic cleavage. Whenever there is a coordinate bond such as through lone pair, pi bond or sigma bond, the electron contribution is always going to be 2. So, these are the 2 rules that you need to remember. Okay. And one more thing that you need to remember is that in why neutral method is more preferred than ionic method is that, say for example, we saw such examples in the last part wherein if you have a bond like this, okay, we saw that we need to use the aromaticity rule to find out the formal charge here, right? Because even though carbon is more electronegative than metal, if you cleave this bond this way, what is going to happen? Here it is going to be a negative charge and this is going to be anti-aromatic. So, anti-aromatic means it is going to be unstable. So, what we do, this is wrong. So, what we do? We have to cleave the bond such that the negative charge goes to the metal and the carbon gets a positive charge, so that this becomes aromatic. So, the same thing has to be applied whenever you do a heterolytic cleavage in such cases. So, if for example, you have the same example. So, instead of formal charge, now we are going to find out the electron contribution. Okay. Now, you see, so you have 2 methods, right? One is neutral method, the other one is ionic method. Now, there are 2 electrons here. In neutral method, you do not have any problem, you just need to cleave the bond homolytically. So, in neutral method, this carbon is contributing how many electrons? 1 electron. But in ionic method, what you need to see is that if you cleave this bond this way, the carbon is going to get a negative charge, it is going to become anti-aromatic. So, you need to see, even before you see the electronegativity, you first thing that you need to see is whether the aromaticity is getting disturbed. In this case, if you cleave the bond towards carbon, the aromaticity is going to get disturbed. So, what is the option? You need to cleave the bond like this. So, the carbon is not contributing any electron. Can you see? Only when you put it like this, only when you say that the carbon is not contributing any electron, this system is going to be stable. So, the carbon is not contributing any electron, only the metal is contributing the electron. So, the ionic method, the electron contribution becomes 0. This is very, very important. Okay. So, that is why we always prefer the neutral method over ionic method, because in competitive exams, they are not going to ask you to find out the electron contribution through neutral method or through ionic method. They are generally, their concern is you need to know how to find the electrons contribution, and it is not going to change your final value in the 18 electron rule. When we see that, you will understand it. So, basically neutral method is more preferred than ionic method, because here you do not have to see the electronegativity, aromaticity rule, etc., and you can simply break the bond homolytically and split the electrons. Okay. So, now what we can do is we will try to do some examples of certain compounds wherein we will find out the hapticity, formal charge and the electron contribution, so that it becomes more clear when I start the 18 electron rule. Okay. These examples, what we are going to do is we are going to find out the hapticity, the formal charge and the electron contribution. Now, electron contribution we are going to find out through both the methods. One is neutral method, which I will denote it by N, and the second one is ionic method. Okay. So, now what we will do is we will do it one by one. Okay. So that it won't confuse you, and once you start to get more acquainted with this concept, you can pause the video and try to do it yourself. Okay. Now, the first one, you need to find out the hapticity. Hapticity is represented by the symbol eta. So, basically hapticity is the number of donor atoms which are from a ligand which are donating electron to the metal. Okay. So, here if you see, this metal is getting electron, one from this carbon and then from the pi bond. Now, pi bond belongs to both the carbon. So, you need to count both the carbons in hapticity. So, the total number of carbon atoms or the donor atoms which are donating the electron to this metal is equal to 3. So, the hapticity becomes 3. Now, the second thing that we are going to find here is the formal charge. So, for formal charge, what I told you, you need to see the electronegativity. Now this bond, so whenever, and one more point that you need to remember, whenever the electron is being donated from a sigma bond, pi bond, or from the lone pair of electrons, then the formal charge will be 0. So for this part wherein the electron is being donated from the pi bond, so the formal charge is going to be 0. But here if you see, carbon is more electronegative, so it's going to have a formal charge of -1. So this part is contributing -1, this part is contributing 0. But the overall formal charge, we need to add both of it, so the formal charge is going to be -1. Okay, and now comes the electron contribution. Now one is neutral method, the second one is ionic method. In neutral method, what did I tell you? You don't have to see any electronegativity or anything. Whatever the bond is there, you just cleave it homolytically. So here there is a metal carbon sigma bond. So you cleave it homolytically, then the electron contribution is going to be 1 electron. Now here it is not a pi bond, it is not a pi bond with the metal, but it is basically pi electron donation. And in such pi electron donation, the rule that I told you is that whenever there is a coordinate bond that is donating through lone pair pi electron or sigma bond, the electron contribution is always going to be 2. So this bond, whether it is through neutral method or ionic method, it is going to donate 2 electrons. So 2 plus 1, it is going to be 3 electrons in the case of neutral method. Now in ionic method, this bottom part is not going to change, right? Because the contribution either through neutral or ionic is going to be same. But the top part, since carbon is more electronegative, both the electrons are donated by carbon. So 2 electron plus 2 electron, it is going to be 4 electron. So this is the difference between neutral method and ionic method. I hope you would have got some clarity. Let us go to the second example. Now you see, hapticity. Hapticity is nothing but the number of donor atoms which is attached to the metal. Donor atoms of the ligand which is attached to the metal. So there is only one atom attached to the metal. So hapticity is going to be 1. Now the formal charge. Now you see what kind of bond is this? It is the lone pair donation, right? Carbon monoxide, it is donating its lone pair. So lone pair is being donated to the metal. So number of so the formal charge is going to be 0, right? Now coming to the electron contribution. One is through neutral method, the other one is through ionic method. Now what did I tell you? Whenever there is a lone pair donation, pi donation or sigma donation, the number of electron contribution through both the methods is going to remain as 2. These 2 electrons only. Okay, you don't have to do any homolytic or heterolytic cleavage. Now move to the third example. First is hapticity. See, hapticity is not the number of bonds. Okay, sometimes you get to do this mistake in your exams wherein you count there are 3 bonds, so hapticity you put it as 3. No, hapticity is the number of donor atoms of a ligand which is attached to the metal. Doesn't matter number of bonds. Okay, so there is only one carbon attached to the metal, so the hapticity is going to be 1. Now formal charge. What is the formal charge? Now see, carbon is more electronegative than the metal, right? So whenever you see, all 3 bonds are attached to metal, right? So all 3 bonds you cleave it home heterolytically towards carbon. So -1, -1, -1. So all 3 electrons. So formal charge is going to be -3. So the metal is going to have the carbon is going to have a formal charge of -3. Now the next part that we are going to see is the electron contribution. One is through neutral method, the other is through ionic method. So for electron contribution in neutral method, it's very simple. You count the total number of electrons. So there are totally 6 electrons, right? So you divide it equally. So 3 electrons for the metal, 3 electrons for the carbon. So basically neutral method, the electron contribution is going to be 3. That's all. So you just count the total number of electrons and you equally divide it between the 2 atoms. So it's going to be 3 electrons. Okay. But in ionic method, what we do, all the electrons will go towards that single atom. So there are totally 6 electrons, right? So this carbon is going to contribute all these 6 electrons. So in ionic method, the contribution is going to be 6 electrons. That's all. So it's basically a triple bond between the metal and carbon. That's all. Now come to this case. Hapticity. So the number of donor atom attached to the ligand, so attached to the metal is 1. Formal charge. So there is a sigma bond. Carbon is more electronegative. So formal charge is -1. Now you find out the electron contribution through neutral and ionic method. Neutral method, what did I tell you? Count the total number of electrons, 2. So divide it equally. So 1 electron. Okay. In ionic method, what you do? Carbon is more electronegative. So give both the electrons to carbon. So in ionic method, the electron contribution is going to be 2. Now you see this example, these two. Okay, now this is, first we'll do this. Here you don't have any aromaticity rule, right? So it's not, basically not an aromatic ring, there is no pi electron. So you can simply do it like a normal case. So hapticity is only 1, there is only one carbon attached. Then you find out the formal charge. Here formal charge, you don't have any aromaticity rule, so you break it towards the more electronegative atom, that is carbon. So carbon is going to get -1. Now you need to find out the contribution through neutral method and ionic method. In neutral method, what did I tell you? Total number of electrons is 2. So divide it equally. So each atom is going to get 1 electron. In ionic method, what you do? Both the electrons is shifted towards carbon. So carbon's contribution is going to be 2 electrons. Now in this case, the aromaticity rule is going to apply because there is a double bond here. And we know that we have seen this multiple times. This cyclopropene ring becomes stable only if it gets a positive charge. So first we will do the hapticity. See hapticity, this carbon is 1 and there is a bond coming from these two carbons as well, this pi bond. So basically how much is the carbon donor atoms? There are totally 3 carbon donor atoms. So eta is equal to 3. Now come to the formal charge. Formal charge we already know. Basically this carbon should get a positive charge for it to become aromatic, right? So basically and this part formal charge is going to be 0. This part is going to get a positive charge. So basically the formal charge of this carbon is going to be +1. Right? The carbon's formal charge is going to be +1. So now we find out the the electron contribution. One is through neutral method, the second one is through ionic method. Okay. So whether it is neutral method or ionic method, this part is going to contribute only 2 electrons. Okay, that is fixed. Now this part, okay, now in neutral method, what did I tell you? You don't need to see any aromaticity, anything. You just break the bond homolytically and then you see that this part will get 1 electron, this part will get 1 electron. So 2 plus 1, it is going to be 3 electron. That's all, neutral method. But in ionic method, we need to see the electronegativity, we need to see the aromaticity. Now as I told you, this part only if it gets a positive charge in carbon, negative charge on metal, it's going to be stable. So the bond will split towards the metal. So how many electrons is being contributed? Only 2 electrons in ionic method. Okay, because this carbon is not contributing any electron, only the metal is contributing 2 electrons according to the ionic method. So the total number of electron contribution is 2 electron only for ionic method and 3 electrons for neutral method. Okay, I hope it's clear. Now we come to this example. See 7, 8 and 9 are 3 same kind of structures, only I have changed the hapticity of the metal. Okay. Now if you see here the hapticity in the first case, wherein you have 2 carbons attached to the metal through a pi bond. So hapticity is going to be 2. Okay, now what about the formal charge? The formal charge here, there is only through a pi electron donation, there is no other sigma bond formation. So formal charge is going to be 0. Okay, and then you need to find out the electron contribution through both neutral method and ionic method. In case of neutral method and ionic method, since it's a pi electron donation, the electron contribution is going to remain the same, that is 2 electron in both the cases. So it's very simple. Now come here. The hapticity here is these 2 carbons are also donating, these 2 carbons are also donating through the pi bond. So totally the 4 carbon atoms are donating. So hapticity is going to be 4. Now come to the formal charge. As I told you, all are pi electron donation only, there is no sigma bond, so formal charge is going to be 0. Now come to the contribution, neutral method, ionic method. Now you see whether it is neutral method or ionic method, if the electron contribution is through a pi bond, we consider it as 2 electrons. So this side there is 2 electron contribution and this side also you have a pi electron contribution. So you need to add both. Okay, so 2 electrons from this side, 2 electrons from that side. So in both the cases, the electron contribution is going to remain 4. Now come here, the hapticity. So basically 2 electrons here, sorry, no, here you have only one bond, right? Okay, okay. So you have only one bond here. So the hapticity is going to be, only 1. Only this carbon is donating its electron. Okay, so hapticity is 1. Now come to the formal charge. So formal charges, carbon is more electronegative, but still you need to see the aromaticity. Now this bond, sorry, this compound would become more stable if it is getting a negative charge here. So it's becoming 6 pi electrons, right? So then it is going to become more stable. So you need to split this bond like this. which is also similar for electronegativity rule also, you will split it like this, and also you need to see the aromaticity. First thing that you need to see is the aromaticity, not the electronegativity. But in this case, both the aromaticity and electronegativity are favoring the electron to move towards carbon. Okay. So, the formal charge here is going to be -1. Okay. The formal charge is going to be -1. Now, what we do? We need to find out the electron contribution. One is through neutral method, the other one is through ionic method. So, in neutral method there is no problem, you just break it homolytically, 1 electron contribution, you put it as 1 electron. In ionic method, what did I tell you? You need to see the aromaticity, and as we saw, the aromaticity favors the electrons to move towards carbon only. So, carbon is only contributing the 2 electrons, metal is not contributing any electron in this case. So, in ionic method the electron contribution is going to be 2 electron. Okay. Now, in the next case, which is also the same type of ligand. So, basically 7, 8, 9 and 10 are same type of compound, wherein I have changed only the hapticity. So, here you see eta is equal to, these two are contributing, these two are contributing, this is also contributing, basically all are contributing. In such cases, basically in exams they will give it also like this, okay, just like how I have done it here, which means all the atoms are contributing. So, you need to just mark the total number of atoms, you just count and put it as the hapticity. So, here the hapticity is going to be 5 because there are totally 5 carbon atoms. Now, come to the formal charge. So, this part there is no formal charge 0, this part there is no formal charge 0 because it is pi electron contribution. Only for this part you need to see, and as I told you, the ring becomes negative, then only it is aromatic. So, the formal charge for this carbon is going to be -1, in that case only it is going to be aromatic. So, formal charge is -1. Now, come to the contribution, neutral method, ionic method. Whether it is neutral method or ionic method, the pi electron contribution is going to remain the same. What is it going to be? 2 electrons from here, 2 electrons from here. So, that 4 electrons is going to be fixed. You see here. So, as I told you, in case of neutral method, you need to break the bond evenly, right. So, 1 electron to carbon, 1 electron to metal. So, 2, 3, 4 and then 1 electron to carbon means the total number of electrons in neutral method is 5. Now, come to ionic method. In case of ionic method, what you do? You split it heterolytically. Here, since this ring is getting a negative charge for aromaticity, both the electrons will go towards carbon. So, 2, 3, 4, 5, 6. Okay. Now, such type of ligands or such type of ligands which can change its hapticity. Can you see? Eta equal to 2, eta equal to 4, eta equal to 1 and eta equal to 5. Such type of ligands are what we call it as fluxinol ligands. Okay. So, the ligands which can change their hapticity are called as fluxinol ligands. That is what we have seen here. You might have heard this term. Now, come to here, come to this part. So, you need to find out the hapticity. So, basically it is a 6-membered ring only in a different configuration. Okay. So, basically how many electrons are present or how many donor atoms are present? 2, 3, 4. So, eta is equal to 4. Now, formal charge. Basically the donation is from the pi electrons. So, formal charge is 0. Now, come to the electron contribution. Now, since the donation is from the pi electrons, whether it is neutral method or ionic method, you just need to count the total number of electrons. So, 2 here, it is going to be 2 electrons from here, 2 electrons from here. So, totally it is going to be 4 electrons, which is constant for both the cases. Now, come to this part. So, it is benzene. So, you need to find out the hapticity. So, totally how many electrons, sorry, how many donor atoms? 6. Okay, all 6 carbon atoms are giving its pi electrons to the metal. Now, formal charge, it is going to be 0 because it is a pi electron donation. It is going to be like this, okay, and all these are going to donate their pi electrons to the metal. That is why we put it like this. Now, we do the contribution, neutral method, ionic method. Since it is pi electron donation, either it is neutral method or ionic method, one pi bond will donate 2 electrons. So, totally you are having 3 pi bonds. So, the total number of electron donation is going to be 6 electrons. Okay. So, this is the electron contribution through neutral method or ionic method. I hope this is clear, and in the next part of the video, I will start with the topic on oxidation state of central method, how do we calculate it, and along with that I will also do the 18 electron rule. Okay. I hope you enjoyed this video. Thank you.